Okay, so we start off from where we this point. This is the point. The probability of accessing a particular microstate can be written as this expression, which is pressure, energy appearing here, and so chemical potential, pressure, and beta being properties of the reservoir. Now, before going further, I want to just remind you of one thing. So basically here, when I was showing, this plot, I wanted to actually indicate that when energy E2 is greater than E1, so I try to draw this rectangle that's bigger than this. Similarly, this rectangle is bigger than this because this size of the rectangle is supposed to be indicative of the volume of phase space. If energy is more, momentum, the number of ways by which you can distribute momentum among n particles, the same number of particles is more, so the phase space volume is going to be more. So when you have n equal to 4, and I couldn't draw it, but the phase space volume will be even more with energy, if the same energy E1, and if you have energy E2, of course, the phase space volume will be even more, and so on and so forth. So that's what I wanted to indicate, but I don't know whether it got missed out. So coming back, so what I've done is take this expression and repeat it here. Now, so this was the probability of a particular microstate, P1, Q1, or rather P1 star, Q1 star, if you like, because if in case you want to say P1 is just the, all the momenta degrees of freedom. So for a particular value, so that's why particular value, Q1, particular value of all the sets of, all this set of positions and momenta, that's one microstate, you have this formula. Now, if you sum over all possible microstates, that will be, of course, equal to 1, because the probability, the sum of all probabilities has to be equal to 1. And to do that, you would have to sum n1 from 0 to infinity, e to the power beta mu n1, right? So this thing. Then energy has to be summed from 0 to infinity, and minus beta e, so e has to be summed, and here you have e to the power beta pv1, right? And then n1 and h1 and so on. So if you notice this quantity, so this is pressure as decided by the reservoir and v1 of the system. So if you take that out, because there's no sum over volume, if you take that out, this becomes e to the power mu beta n1 sum over all particles, and this is nothing but the partition function with n1 particles, right? And there is a sum over n1. This is nothing but the fugacity, or if you like, this is the grand canonical partition function, sum over all particles e to the power mu beta into canonical partition function with n1 particles, sum over n1. So what you get essentially is 1 equal to minus beta pv1 zgc. This essentially means that the partition function, grand canonical, the value of that, you need to evaluate it. It's e to the power beta pv1. If you know the pressure, you know the value of the grand canonical partition function. And in that case, pv1 k by kbt equal to ln of gc. So that's an important relation. That's an important relation to keep in mind, which we're going to use, of course. So I have just repeated the same expression. The partition function of GC is fugacity to the power n1 z, canonical partition function n1. Now, if you wanted to have the probability of accessing all microstates of system, this is the smallest system in contact with the reservoir with n1 particles, then of course, the denominator will be the grand canonical partition function, but the numerator will be when you have n1 particles, right? So the probability of accessing those microstates is, of course, the probability of accessing those microstates, I think I wrote down previously, e to the power minus beta E1 into e to the power beta mu N1. That's for one microstate. And if you sum over all i's, all the values of energy and all the different microstates corresponding to each value of energy, but keeping N1 particles, right? So then this sum is essentially Zn1c, yeah, because you're keeping N1 particles, e to the power beta mu N1 into the grand canonical partition function, where of course you have also a sum over this quantity, right? So that in turn can be written as Zc canonical N1 fugacity to the power N1 upon the grand canonical partition function. And then the average number of particles in that case can be calculated as N1. Probability of having a having all microstates with particle N1, which is just as we calculated, we are substituting it here, and N1 goes from 0 to infinity, right? So to get an N1 here, what you could do is take a derivative with respect to Z, and that will give you N1 Z to the power N minus 1. And then you multiply by Z, you will get again N1 Z to the power N1, right? So that's how, so you're basically writing this as a derivative, right, with respect to del del Z, and thereafter upon the grand canonical partition function, which you can write again. Of course, you can take this derivative out of the summation, because this is e to the power beta mu, that is not changing when you take different systems, when you take systems with different number of N1 particles, so that's intact. That's why you can take it out of the summation. So what you get is this, and this is the del del of grand canonical partition function. This summation is the grand canonical partition function. You are Z into del del Z, right? So that's what you can do, which in turn can be written as del del Z of log ZGC. So this is also a relevant. So this is so here also you are calculating the partition function, but calculating it by taking a derivative with respect to del del Z, right? That which is the fugacity. So Z into del del Z. Previously, you took it with respect to alpha, which is minus mu by KBT. So just to summarize all the relations, you can calculate the average number of particles by as Z del del Z, which we just showed. The average energy of the system, which we showed in the previous class, can be written as minus del del beta log of the partition grand canonical partition function, and this is the fugacity. This is the curly Z. So it is to be differentiated when I have ZGC. That's the grand canonical partition function. ZC is the canonical partition function, and curly Z. So sometimes I do a curly Z here, or sometimes this straight line I make it a bit curly. VT. So that's the formula. So CV, of course, can be calculated as del U del T. So once you calculate U and you differentiate with respect to T, then you can calculate your CV. And in general, dQ by T is ds, right? This is the TdS equation. And if you know CV, and for different temperatures, so CV can be a function of temperature also, and we shall see that soon. So if you CV by, so this dQ can be written as CV dt by T equal to ds. If you integrate the two sides of the equation, and at T equal to 0, you assume that the number of microstates is 0. I mean, everything is frozen, all the particles are frozen. I mean, if you could reach, of course, you can't reach T equal to 0, then you would get this relation. Actually, what Sakut and Tetrode did, is take a gas of sodium or something like that. I've forgotten what it was, and manage to measure the gas, the CV at various values of temperature. Of course, they can't reach zero temperature. But if you integrate from 0 to t, and if you have this measured value, and you do this integration by hand from whatever low temperatures you can reach, then you get an explicit function value of S. Now, this S could be related to the theoretical S, which was calculated for a ideal gas of particles. And since you have an exact measurement of S, assuming, of course, you can't reach your t equal to 0, then from there you could somehow calculate that the H in the expression for the microcanonical ensemble, I mean, whatever, or the canonical ensemble, the H as in the volume of phase space, that he identified or measured it to be the Planck's constant, right? So I was supposed to do this Sacco tetrad. I'm not doing it in detail, but I just told you this was the basic principle. This was a diversion. So now, if you have the Gantt canonical partition function, you can also calculate the free energy of the system. Now, the free energy of the system is typically calculated in a canonical ensemble when the number of particles is fixed, right? Uh, but the point I'm trying to emphasize is that you can calculate whatever your grand canonical partition function, if you have a grand canonical ensemble or a canonical partition function, and from there get other quantities. Like, for example, if you had a canonical system and you could calculate your pressure, you could calculate your pressure, you knew your volume, and by kBt is actually the log of the grand canonical partition function, right? So even in a canonical system, you can use this relation, of course, um, yeah, to calculate the grand canonical partition function. On the other hand, if you have a grand canonical partition function, then you can calculate the free energy of the system. Of course, the free energy is going to change because number of particles is going to change. But what you are calculating when you say that you are calculating the free energy of the system, what you mean is you are calculating the mean free energy of the system, and that can easily be calculated. ZGC, the general expression for ZGC is n equal to 0 to infinity, e to the power beta mu n, or fugacity to the power n, there's a summation over n, canonical partition function with NVT. And this summation would have very low contributions if there were large deviations from n bar. You just say that the maximum contribution to this grand canonical partition function is from from the term when n is equal to n bar, other terms in the summation when n is not equal to n bar, they contribute, but that's very less. And then you say that, okay, so this summation is replaced with other terms being contributing less by e to the power beta mu n bar. Here there was a summation. This is replaced by n bar, and then ZC n bar VT, right? And this is the canonical partition function. If you take its log, then you can get your free energy of the system with n bar particles, or with n particles, which is equal to n bar of the grand canonical ensemble. Basically, all that you are taking is log of, so basically this is what you get. So this is the e to the power, yeah, I mean, you can just try it out. You can just take the suitable log minus kBt blah blah, and you will get the free energy, right? So minus kBt log z, capital Z, is equal to the free energy, and that is now expressed in terms of the grand canonical partition function kBt n bar kBt log in terms of fugacity, chemical potential, right? So you can calculate, even in the grand canonical, you can calculate the mean value of the free energy of the system in this manner. The next thing which I want to is showing is basically we got this expression for the mean number of particles, where you're taking z del del z, ln grand canonical partition function, and that can also be written as del del beta mu. Remember, we already showed that the beta mu equal to alpha, and it came with a minus sign. But if you are taking a derivative with respect to beta mu, that is going to give you the average number of particles. This quantity, this can also be shown as del del beta mu is by this. So del del, where you are changing your variables to fugacity, and correspondingly, yeah, your del del e to the power beta mu. So this is fugacity, and then you get this z del del z, right? So this is this term, which is this term. So you can either write this, or instead of beta mu, you could write alpha, and then you would have a minus sign in front. So similarly, you can write, well, this I have, I think, repeated quite a few times. Now, in thermodynamics, what you can always talk about is the average number of particles. But in statistical physics, what you also have access to is the fluctuations in the number of particles. Fluctuations in the number of particles can be shown to be the mean number of particles in the system into kBt, into thermal compressibility. So isothermal compressibility, and B here is the volume per particle. Okay, so this I will just do it in a separate recording, but so it's a bit algebraically long, but this is a relation. So what I've done is, in the last two slides, written down all the relations, and just to remind you, the probability of accessing a particular microstate P1 Q1 and with N1 and E1 can be written as e to the power beta mu N1 minus beta P V1 and beta E1, right? So that's one way to write it. Of course, the other way to write it is also there. But this is a more obtuse way of calculating. So we actually replace this by doing a simple algebra. So this was the starting point, and we replace this by this expression, right? With beta E1, because that ratio was turned out to be beta mu N1 minus beta is the probability of a microstate. You can calculate the probability that a system has particle energy E1. You can calculate that the probability that a system has particle N1, and energy can fluctuate all over. So you have to take the suitable sum in the numerator, and in the denominator what you will have is the partition function, right? So I'll end this lecture here, and what we'll do in the next part is basically do this, show this algebra, which is basically worked out path here. So the first thing